to tell them, as we know, we started an expert lecture series from April this year. And the first lecture was delivered by Professor Stephen Newman, former professor, University of South Wales, Australia. He spoke about galvanized bars. Then the second lecture was on 14 June by Professor Krishna Reddy, University of Illinois. We talked about NCA and sustainability in construction. Then on 4th July, Professor John Provis from University of Sheffield, we talked about innovations in types of cement. So normally these lectures were in the online mode, and today's lecture will be in the hybrid mode. We are live streaming on our YouTube channel and video stream as well. So friends, today we have a very distinguished speaker, Professor Venkatesh Kodur from University of Michigan. Although he came earlier also, but we always interested in listening to him, the new developments in higher structure, engineering, and other issues. So first, we would like to present him here. Okay, I request Ms. Paula to present your booklet. Now I request our director, Professor R. Pradeep Kumar, to give his welcome speech.
On behalf of entire CSIR-CBRI family, I warmly welcome Professor Venkatesh Kodur for giving this lecture as one of the lecturers in this monthly lecture series by eminent personalities. We have spent almost like maybe 3 decades or more in that area. Probably yours is more than that definitely. So to tell you, as you already know, but I just wanted to tell you briefly that CSIR-CBRI was constituted as one of the constituent laboratory of CSIR in 1947. So we have the history of like 75 years in the service of the nation. We are working in almost all the aspects of building construction, so A to Z. So we have groups in the areas of architecture, planning and energy efficiency, geotechnical engineering and geohazards, building materials, advanced concrete, composites, steel, and then heritage structures, then fire safety engineering, and all related areas of building. And today, coming to today's topic, is fire safety. What I feel is this is not, it has not become yet the mainstream in civil engineering and mechanical engineering, because these are the two areas, and chemical engineering also. So these are like some of the branches which can own this and make it integral part of the curriculum. Unless until we create human resources in this area, we do like whatever operations we are doing, that will be in a reactive mode only. So in CBRI we have like what we feel is a state of the art experimental facility, and whatever shortcomings are there in that to catch up the fast pace in which the world is changing, that we are ready to do. That is one thing. And at the same time, we want to lead that effort in preparing a white paper or policy document for fire safety in the country. So that is the aspirations we have, and in that your expert lecture, I hope it will help and motivate several of us in taking up our research in that direction. So with these few words, I once again welcome you for this international lecture series. Thank you, sir.
Okay. Now, I request Dr. Panji, head of the fire research group, to, although we don't need his introduction, most of us know, but just for the sake of formality and those who are new in the institute, I request Dr. Panji to introduce the speaker. To Dr. Karade. I welcome you on behalf as well on CSIR-CBRI. I welcome you once again, sir. Today, with us Professor Venkatesh Kodur. Professor Venkatesh Kodur has done his BSc in Civil Engineering from the Bangalore University, India, 1985. Then he has done MSc in Structural Engineering, Queen's University, Canada, in 1988. And then PhD in Structural Engineering, Queen's University, Canada, 1992. Professor Venkatesh Kodur is a University Distinguished Professor and Director of the Center on Structural Fire Engineering and Diagnostic at Michigan State University. He is an internationally recognized scholar for his contribution in civil and fire engineering field, and his research accomplishments have had major impacts. He has developed fundamental understanding of the behavior of materials and structural systems under extreme fire conditions. The techniques and methodologies resulting from his research is instrumental for minimizing the destructive impact of fire in the built infrastructure, which contributes to cause thousands of deaths and billions of dollars of damage each year in the US and around the world. Many of these design approaches and fire-resistant solutions have been incorporated into the various construction codes and design standards in the US and around the world. Professor Kodur has an outstanding record on international research initiatives and collaborations and has collaborated with top researchers and prestigious organizations from about 2 dozen countries to produce high-quality deliverables. He has published more than 500 peer-reviewed research papers and conferences. He has given numerous keynote presentations in major international conferences. He is one of the highly cited authors in civil engineering and fire protection engineering discipline, and as per Google Scholar, he has more than 90,000 citations with an edge index of 77. Professor Kodur has served in various leadership positions, including as chairperson and associate chairperson of the Department of Civil and Environmental Engineering at Michigan State University, and as chair of various technical committees of leading professional societies and on editorial boards of leading journals. In recognition of his contribution, he has been cited. He has been elected as fellow of 6 institutes and academy like Canadian Academy of Engineering, American Society of Civil Engineers, American Concrete Institute, Indian National Academy of Engineering. Professor Kodur is also received of distinguished awards such as NATO Award for Collaborative Research, Government of Canada, Outstanding Achievement Award, and unauthorized Scholar Award. Professor Kodur also holds Infosys Distinguished Visiting Chair Professor appointment at the Indian Institute of Science, Bangalore and Government of India. Vajara Faculty Award for Collaborative Research at the Indian Institute of Technology, Delhi. Most notably, Professor Kodur was part of the Federal Emergency Management Agency and American Society of Civil Engineers high-profile expert team that investigated collapse of the World Trade Center building as a result of September 11, 2001 terrorist attack. With this brief introduction, I will invite Professor Kodur for his lecture. But before this, I believe that we will understand some, at least some kind of Hindi, because our professor is from itself from South and he has a equivalent command of Hindi and English. So I invite Professor Kodur with a few lines from Hindi poem. हो गई है पीर पर्वत सी पिघलनी चाहिए, हो गई है पीर पर्वत सी पिघलनी चाहिए, इस हिमालय से कोई गंगा निकलनी चाहिए. You are invited to the
Question.
Good afternoon to you all. So it's a great pleasure and honor for me to be back at CSIR-CBRI, after about 5-6 years, right? So it is like, coming back to the place where I had a few projects here before. As you all know, I have delivered some seminars and presentations here. But I meet your directors, group leaders, colleagues, scientists in various forums. They were inviting me for the last, since almost 1.5 years after the COVID subsides. So it is good that this opportunity I have. I would like to thank the director here, as well as Pradeep Kumar, Dr. Arpal Singh, Dr. Benty, as well as many of his fellow group leaders and the scientists for making this possible, right? So I received a warm welcome wherever I go around the world, but never I received a poetic welcome. So thank you very much for that, making it unique. Okay, so can you all hear me?
Yes. Yes.
Okay. So today's presentation is on conditional assessment and refurbishment of fire damage structures from reconnaissance to advanced analysis. Basically, I'm presenting this, still it's primitive, just like fire resistance design is prescriptive primitive. Post-fire damage assessment is much more primitive. Somebody goes in, looks at it, based on, they have no idea what fire is, even they don't have not studied anything. They know good structural engineers, but you need to know about fire as well, or what kind of damage that occur in the microstructure level. So they go and they do this. So it is much more primitive. And the idea, this field has not evolved. At least fire design, you have some performance-based documents and stuff. This field is not engineered at all. And you need to engineer it to go from reconnaissance first when somebody goes there to retrofitting stage. So that's the idea of this presentation. As mentioned, I was part of the 9/11 investigation. Many of the buildings suffered major damage, as you know. 9 buildings either collapsed or partially as good as collapsed. Gone. 18 buildings suffered major structural damage. 18 buildings. 40 buildings suffered minor structural damage. 60 buildings needed cleaning around Rumsi. Much of that is fire damage. No documents, no guidelines, nothing to investigate and to bring back the buildings to occupancy. So that's the motivation for me. That's when I thought about this. I developed into a research area over the last 10 to 15 years, right? So quickly, I'm going to give you some background information to fire hazard itself. You all very well know that. And why we need to evaluate through engineered way for this residual capacity or fire damage, extent of fire damage. Then present what kind of post-fire damage assessment, how forensic engineering can be put effectively used. Then methodology for damage assessment, I'm going to look at it, especially the calculation methods, right? So how that can be still not fully developed, but how it can be used. And because of time, I don't have time to go into case studies, but recently we did one in Brazil. I'll just mention, and there is a paper you can look at it, right? So fire represents a severe hazard and threat to the built environment. It causes thousands of deaths and billions of dollars of damage each and every year in all countries around the world. And you see the statistics for the United States for 2021 published by NFPA, for example, 1.35 billion fires, right? Leading to about 3,800 deaths and $16 billion of damage, right? This is the direct damage. Indirect damage, if you consider some repairs, retrofitting after that, it comes to $60 billion, right? So many of these fires, right, results in number of injuries as well as property damage. Now, when it happens, it is the most severe condition a structure can face. Earthquakes are severe, losses are severe, impacts are severe. Fire can represent much more severe and lead to collapse in rare cases. It can start as a short electric circuit or some cooking fire. In US, the most cause of fire today is electric cooking fires. In India, it's electric short circuit. If you go to Russia, it's much more pumps drinking. You know, the fire starts in the pumps and stuff. If you go to Eastern Europe, it's the old age homes. That's where the most fire problem is. So depending on the country and culture, so that is much more to play. That's very important in developing a policy for a country, and you cannot adapt from somewhere. So basically, it can start from an electric short circuit somewhere happening, or as a secondary event also fires can start. You take a truck hits a bridge. The bridge is designed for impact load, but it's not designed for fire. A blast happens, a lot of times it is designed for fire, but not the fire. Typically, blast is followed by the fire. Earthquake, New Zealand earthquake, Kobe earthquake, US also, San Francisco earthquake, fire do much more damage in some cases than the earthquake primary. 9/11, when it happened and the buildings came down. We did 1 year investigation. Our conclusion is the towers would have been standing today if there were no major. The impact is not the one which brought down the towers. It is the fires which brought down not only the towers, surrounding building sites. So fire, and remember now Roorkee is flooded everywhere, including in the campus. In New Jersey, there was a hurricane followed by huge rains. In 2012, it's called Hurricane Sandy, one of the worst hurricanes we had. Huge flooding happened outside New Jersey next to the Atlantic Ocean, and there was a flooded, basements flooded, and the pumps couldn't handle. And then what happened? There was one electric short circuit in 1 hour, spread to 2,000 houses, burned away in 1.5 hours. 1 hour, 90 days, 2,000 houses, each worth $2 million. These are beachfront homes. So imagine the damage. So even after flooding, people laugh when I say this, right? Fire and short circuit, anything happen, it can spread widely and quickly. Now, all this is, we have a number of measures we put in because we cannot prevent fires. So building codes do address this. They put in active systems such as sprinklers, leak detectors, smoke detectors, exit paths, followed by structural fire safety. You have to be your structure. If you well compartmentalize, if the fire stays locally, it's easy to fight the fire. It's a piece of cake. But if it spreads quickly, then it's very hard to even fighting the fire. Firefighters also cannot do much damage when it spreads to the whole floor or 2 floors or 3 floors. So I think from that point of view, we put in a lot of measures. Because we are putting all these measures, these days what's happening is structural collapses due to fire are rare. It happens in 9/11, number of cases I will show you. But what happens is when the fire pulls down, the structure has to be reoccupied. Right? So for that, you have to assess the safety, you have to assess what repair is to be needed, and you have to assess how much insurance claims are there. For that, residual capacity or post-fire damage assessment is very much essential. Now, it's not just US alone. Look at here the statistics. India has the worst record right now from the fire safety point of view, which is very unfortunate. So this is the statistics published by Geneva Institute of Statistics, and according to that, between 1914 to 1919, there were 23,000 plus deaths in India every year on average. And China is next, 10,000, and other countries. But if you see countries such as South Africa, which is smaller, this is 1.7 is the number of people dying per 100,000 people a year, which is high. But if you see some countries, it's much higher. Similarly, property damage is very high in Indian conditions. So this is a national loss. Also, as you can see here, I don't want to go into all this. People say fires are rare. Not true. Number of fires do happen. And these are some of the major fires in New York City. Just to tell you, fires affect weaker sections of the society much more than rich people, well-built people, and especially women, pregnant women, or aged people, children. So fire is bad. So from national policy point of view, this is very important for organizations like CBRI or anybody to protect the weaker sections of the society. So if you see in this house in New York City, it is a 90-story apartment building, a poor neighborhood. And in this, what happens? There was winter, and we have fully air-conditioned, fully heated facilities. But to save money, they were just putting local heaters and warming themselves up. Huge carpeting was there. Quickly, the fire spreads to the carpet. Fire department comes in 14 minutes. By then, 9 kids, 8 children, adults, dozens were injured. So a lot of loss of life. 4 days before that, same thing happened in Philadelphia. Right? So the fires grew up there. And you know what happened in 9/11? As well as I was part of the investigation for a Technical University of Architecture building in Delft, Netherlands in 2008, when this building, a 14-story building, a coffee kettle, somebody didn't turn off a student. He goes home, graduate student. So then there was a sink, the pot heats up, it quickly spreads, explosion happens, and then because of the short circuit, then the water main is broken. Fire department comes to fight the fire after some delay. They couldn't fight the fire because of the spalling that was occurring in this one. And then the whole building, luckily the firefighters were called out just 2 minutes before. Otherwise, about 60 firefighters would have been dead. They just came out and the building collapses. 150 million euros was the payout. And the reason for that is lot of leftover wood in the building from the farmer. Concrete, they didn't remove that. Second, lot of architectural studios for the students. Architecture, you have a department here, they know. Lot of architectural studios. So this is how fires could happen. But if you look at this building, it will tell you the importance of much more on the residual capacity assessment and forensic engineering. This building, you might have all read, this is in London, inside the London, is 24-story concrete building called Grenfell Tower. Very nicely built building, modern part of the building, apartment building. Again, here, there were a lot of poor people. Poor means, a lot of refugees coming from Syria house. So they don't know English language when they came in, though it was in London. So what happened is one day, a faulty electric wire in a bridge catches fire, bridge, a small bridge, and fires suddenly, this is very rare, fires spread rapidly, fires do spread but slowly, but because of the facades, what they put in the cladding, exterior cladding. These days we are putting too much of this in our building for energy savings, for sustainability, environment. Lot of them are highly combustible. They are not tested. There is no regulation for putting outside for cladding and stuff in many of the codes and standards. Fire spreads, they couldn't get out. So they were asked to stay in place, unfortunately. They were told not to come down because we will fight out the fire. The fire department thought that they could fight the fire, but when they could, they jumped to safety. By the end, 79 people died and hundreds injured. But now the fire department wouldn't want to enter. Why? The stability of the building was calling into question. And they called the structural engineers, they called the fire engineers. Can you tell us whether it's safe to go or not? No, nobody could tell because we don't know. Because the reason is, forensic engineering is not there for fire damage buildings yet. So nobody wants to take responsibility. You say something happens, right? So at that time, they didn't go for 3 days into the building of people trying to pick up the bodies. So this is the state of the art in 2022, right? So that motivates this kind of research. Now, it's not building something. Bridges are becoming a problem these days. Just 2 weeks ago, I sent an article to Dr. Pandey. It can circulate to you. This is very important for India, as I see it, for your metro stations or subway systems, which is coming all around the country as well as in the north tunnels. So this is a steel girder bridge, and this is the #1 bridge in the United States, the #1 highway going from Florida to almost New Jersey and beyond. Like Boston, basically. So Massachusetts. So this big high tanker was going, and it tries to enter the highway, the exit, and it spills and it hits the bridge. Huge fire starts, and fire department comes in because it's outside of Philadelphia. They couldn't fight the fire, right? So the spans of the bridge collapses. Much damage. Not only that, the highway was closed the expressway for next 3 weeks till temporary measures on both sides. So bringing down the supply chain, everything, travel, everything to a standstill. So number of bridges, even Europe, you see that in China recently there were bridges. So rapid assessment is very much needed in these cases, either to evaluate safety, retrofit, what strategies to be adopted, and right now we don't have this. So this is another interesting story. This is I-85 bridge, Interstate 85. This is a major bridge outside of Atlanta, Georgia. So in this case, what happens on March 30th, 2017, the bridge was in a very good condition. We inspect bridges every 5 years and give recommendations whether it's in the good rating, just a KBCD rating. We rate them, A is good, B is bad. So this was in a very good rating just 2 years before that. And after that, what happened? And there was some drainage issue, water logging inside. So they brought in a lot of PVC pipes and assembled down for repair. They brought in March 1st week. That's what happens in the US. All the repairs and highways start after May when spring season starts because it's too cold to work outside. So on March, it was very cold evening in Georgia, Atlanta. So some homeless person, he comes with beer bottles. He wants to warm himself up. He puts some rubber, takes all the paper and everything. He starts a bonfire to warm himself. It was cold underneath the bridge where the pipes are there. He was drinking. Suddenly, he might have lost consciousness. Quickly, it spreads to the pipes, PVC pipes. You know how dangerous it is. Huge pipes. He runs away. So somebody who sees the smoke and driving, they call the fire department. So they come in. They started to fight the fire. Can you see the small in there? It's real, right? Within 1 hour spans of the bridge collapses. And so Delta, Atlanta is the world's, used to be #1 in terms of traffic around the world. That's Atlanta is the largest airport. Next is London, Heathrow. So next week or two, flight attendants, there are about 50,000 flight attendants, flight personnel who work at the airport. They couldn't get to the airport. That was a major highway, expressway, all flights delayed, cancelled. Believe it or not, I was going to China. I was waiting for the flight to come from Atlanta to Detroit to go to Shanghai for a meeting. They called me whether they can open the bridge for traffic. If the part of US, we cannot give any advice because it's not of litigation, then they can sue. I said, who am I? I'm not God has let me something, to recommend opening or closing bridge. So there are no methods in any highway guides or building codes or something. So that's how significant it is. And when it comes to India, you know more than that. I follow Indian newspapers whenever I get a chance, or news channels. Hospital fires is becoming much more common in India, which is very, very unfortunate. Right? It's hard to evacuate people. It's hard to not only evacuation, but after that, what do you do with the patients? Where do you place those patients? Right? So from that perspective, I was in Gunma recently, and I heard there was a fire in the hospital attached to the hospital building. Both specialists, husband and wife doctors, both died. Their relatives, two of them died, and their servant died. In a short circuit, the fire started. Right? So this was in this year itself. So there is significant number of fires in India. Now, when it comes to example, how important the fires are in India, you can look at no more than this Surat Takshashila Arcade building, where it's a coaching center for people taking JEE and other exams. So in this building, it's just a 4-story building. And look at what happened. Electric short circuit, number of students were there in the coaching center. The fires these days, because of the type of materials we have, combustibles we have, because of 5 layers of curtains you use in the home, because so many shoes we keep as youngsters, or for each thing we need, our fuel load used to be very less, right? All this leads to sudden burst of fires. Very quickly they spread. Before it would take, we did tests with undergraduate laboratories for US fire departments to see how far modern buildings, structural members collapse in 6 minutes houses, whereas previously the same structure, same contents used to take 30 minutes to experience the collapse. So that's what modern materials, concrete, steel, wood, the FRP, modern the material is, poorer the fire resistance. So anyways, in this building, many of them were teenagers, as you can imagine, 24 deaths, right? And they had couldn't staircase at this stage, right? Emergency gate, right to go, the staircase itself was adding fuel to the fire, right? This is the scenario with fire safety, right? So after that, the structure itself was okay, but still it has to be evaluated, so residual capacity is very important. So what do we do currently? We put in lot of measures in building codes. Not that we don't do anything, such as I mentioned to you, active systems such as sprinklers, heat detectors, smoke detectors, exit bars. Some of them work, some of them don't. But second thing we put in is fire resistance, which is basically a structural member has to stop the fire there itself, which is compartmentation. The walls and floor systems are flat. Our columns and beams, they should have stability through for 2 hours, 1 hour, 3 hours duration, depending on the height of the building, size of the compartment. So we put in this. So, but we don't have anything for bridges, very little for tunnels, tunnel linings, for example, and also there is no specific studies when it comes to metros and some of this as well. That's where currently it stands. Now, if you see that, all these measures we put in, this is where your sprinklers see. This is how fire grows in a room, typical. Look at here, slowly, it takes some time. It doesn't grow very fast. But after that, once everything starts burning, this is called the ignition phase. This is called the growth phase. It grows, flashover happens. Then whole room burning is flashover. Then you have fully developed fire, and then it dies down. So where does the structural fire safety comes in? Here. Nothing happens to the structure here. Up to reaching the fully grown fire, Nothing happens to your structural elements. It's only sprinklers, leak detectors, smoke detectors. They are the ones which play a role. Even when they don't play. If they put out the fire, that's good, right? So then, if they don't put out, then you have growing into the phase of the structural. So at that time, structure has to withstand that fire. Now, so in this case, what we can conclude from this is fire is a rare event, as you can see. I mean, it doesn't happen thousands of fires. It's still there. When it occurs, only a subset of fires they grow into. Otherwise, they are put out by the firefighters or sprinklers or automatically. They die down a lot of fires themselves itself if there is not enough oxygen or the fuel. But when they go into a small subset of fires will do damage to the structure. And a much smaller subset will lead into collapse of the building. But when they do the damage, whether to get back to that building, whether to open the bridge, whether to, how much strengthening has to happen, how much to put back the capacity to the original level, you need assessment first before even record. How much insurance damage you need. Okay, so that's very important. Now, there are not that fire damage is not as easy as we say by looking at it. With experience, you can do a little bit of that, but otherwise you need proper engineering because it depends on number of factors, such as, for example, how severe was the fire, how long it burned. Common sense, kind of concrete can withstand better than steel or wood or steel. No, right? So then, kind of structural detailing, how much load was there during the fire or before the fire, or how much reserve strength. A lot of times we over-design the structure very commonly as most cases. You need to know higher the over-design. These days it's reducing. That's why what the structures behave well. More the reserve capacity, better it is from the fire safety point of view. All this is important. Now, especially today I'm going to talk about, we have done the same thing for steel structures, but a lot more focus on bridges because steel bridges are much more vulnerable. We don't put fireproofing. I'm going to present most of the stuff today is for concrete structures. So concrete is a very good material. As you all know, it has high fire resistance and it can withstand the fire because of its low thermal conductivity, high capacity, and slow degradation in strength. So this is, for example, concrete. This is steel. This is wood. This is a barbie. Okay? How the strength degrades with increase in temperature. So from this point of view, concrete, you can expect very good performance during the fire and after the fire. So when the fire dies down, concrete structures do have good level of reserve capacity to retrofit and strengthening. Now, just to give you how do I know, this was a 9/11 investigation I was involved in. This is one of the buildings, not our towers, 90 West. This is a famous building, 23-story building, built in 1907. Right? So there was no amount of debris when the fire spread. It went into this building and it burned on and off for about 5 days on and off the building because there was no firefighting, nothing was available, ground zero. There was no water, no power, right? Nothing was there in ground zero in terms of anything to fight the fire. So nobody wanted to fight the fire. There were bodies stuck underneath, so they were pulling out the bodies. Right, when we were there, and it's unbelievable body parts. So they were focusing much more on that than those ones, and also opening the area for the stock market stuff. But anyways, this building was on and off. Nobody was inside the building. But even after 5 days, it didn't collapse. Look at the steel frame building. This is the Tata World Trade Center, which is opposite to the two towers. A nice steel frame building, and this again there was a fire which spread into this building on and off. It burned for 8 hours and it collapsed in 8 hours. Right? Steel frame building. So this gives us a good idea that concrete buildings do have much higher even fire resistance capacity. Now, and quickly, this was a fire in Turkey just recently, as you can see in April, I believe. And in this building, it's 8 floors high. This is a rich condominium building. And you can see here, concrete buildings. I wanted to show you how it works. Anyways, it doesn't work. So in this building, For example, when the fires spread rapidly and quickly, 1 for 8 hours firefighting was happening, many people were evacuated, nobody died luckily because quick evacuation happened. But one important thing is it didn't collapse. Now they are retrofitting this building and bringing it back to occupancy. So this shows the importance in concrete structures to have. So I already mentioned quickly, why do we need to evaluate residual capacity? To assess the post-fire damage assessment, whether it's safe to send people inside, to send equipment, to send first responders inside, even to look for bodies. So you need to ensure, short-term and long-term stability is there. Second thing is, if you want to repair, what level of repair is needed? You cannot put, it's not just like covering up cosmetic damage. You need to know how much rebar still have the strength, how much concrete falling has happened, whether to bring back. You need to do that. And then insurance plans. A lot of times buildings are insured most of the countries. So when you want to pay out, insurance has to estimate that and approve that damage. So this is very important. Now assessing this residual capacity, what's the state of the art? There is very limited knowledge around. In fact, I think because as you can see, there is heating phase, there is cooling phase, there is residual phase. That means it takes 4 to 5 days in a concrete structure for it to attain its full strength back. Steel structure within a day, but concrete structure when it goes down inside, because the number it is, concrete has a very, very low heat capacity, very high heat capacity. It doesn't give out heat quickly, so it takes recovering is much higher. The second thing what I want to tell you is very careful because CBRI is involved in a lot of this thing and when you advise even NDMA. So you cannot get into a concrete. Switzerland, there was a building, parking garage, 7-story in Geneva, and the fire was put out in the night. It's a with concrete structure. So what happened was they went inside and they fought the fire, they came back. Nothing was fine, they went out. So next day they have to write the first information or investigation report. The firefighters are responsible. So they went in. After about nearly 18 hours, both structure collapsed. So the cooling phase, not a residual phase, I call it. That's why in London they didn't want to go. Residual phase is much more dangerous from the point of view. A lot of times firefighters, they are not knowledgeable because we are not teaching many of this in our courses and stuff. So residual phase is more dangerous than even the heating phase sometimes. Heating phase, they are covered, they are visiting, they are far away. Residual phase, they are very big. The structure is cooling down, it puts too much stresses on the connection here, and it's recovering, and it's too much tension forces. It's not designed for that, it comes down. Okay? So anyways, so from that point of view, there are very limited guidelines. Only thing, use case, there is a policy document from 2007. How to assess the residual capacity. The engineering is not less, but just to give an idea of what's the responsibility of the engineer, what's the responsibility of the owner, that kind of stuff is their policy document. So then there are lack of engineer advanced analysis approaches. So this how typically behaves. If you have a building here, let's say this is under fire, that's the beam. You want to see how much capacity it has. So this is the fire in the room itself in that compartment. This is the temperatures in the rebar inside the concrete. You know where the rebar is. And if you see here, this is the big depth of the concrete beam. Okay, somewhere there. Now, the deformation, this is the first 15-20 minutes, nothing happens. Then slowly deformations increase. But since it's cooling, with certain lag, it starts to regain its reflection, regain its strength. Then it goes up. This is the residual. So finally, you end up with residual deformations, and that's the one, when you have residual deformations, the capacity is very complex to model this. It's not easy. So we have done a lot of work over the last decade or so, as I mentioned to you, on this subject with significant funding. So what did we do? First, we looked at state of the art, as I already showed you, identified the knowledge gaps. Then came up with a classification system for assessing, for damage assessment, right? Then they did a lot of experiments, and then we developed methodology at different levels, depending on different extent of damage which have different classes of damage. Okay, and then did some practical applications and repair strategies. So first first of all, let me quickly show you some experimental studies. Doing residual test, residual capacity test is different from fire resistance test. You cannot do it in one shot. You have to do 3 stages of analysis or experiment. Just before the fire started, you need to know how much is the capacity the structure has. This building was built in 1947. Today, we don't know what the capacity of the beam really. Even at that time, if you look back at drawings, you cannot take it at the face value because this real reserve capacity based on this you have to establish. Then you have to subject that beam to fire involving heating, realistic fire, not the standard fire. Heating phase, cooling phase, whatever is present in the room. Then once you do that, then after the cooling down, then subject that beam to structural test to find out how much capacity. So 3 stages of analysis is required in doing this experimental procedure we developed in 2013 and 14. So if you see here, so this is the first stage. First stage is this. So you need to apply the load of those beams to whatever was the service loads, not the full design loads, not the ultimate capacity. You need to subject them to service load, find out how much deformations of the service load, how much the deflections the beam has. Then you carry out the fire resistance test on the beam by subjecting it to fire, right? And it is, we look at this, this is the fire load. Right? Just like it was in that room, it depends on the fuel load. You can calculate the fire costs. I'll show you quickly. Then this is the temperatures in the rebar. This is the temperatures in the concrete. At various places you need to measure using the thermometer instrumentation. Then this is the deflection. You look at this. This is the one subjected beam. We tested these 2 beams. One with a short arc fire, sorry, long arc fire, and short medium fire. So that means, as you saw, there were 2 fires which we looked at. As you see, this is short arc fire, this is long arc fire. Okay, so we subjected that. Then following that, we established the residual capacity. The one which is long arc fire is a lower capacity than the short arc fire, the low deflection one. Then you can estimate what the capacity is. Following that, tests which were useful for model validation and number of things. Then we started fire damage assessment procedure we developed. So if you go to inspection, everyone used to ask me before, give us some charts. What is what? I mean, how to inspect this? We said as soon as you go with some experience, with some background, you can assess as soon as you go to the job site on the second day or third day, you need an engineering degree or engineering background, engineering expertise. You can divide it into 5 classes of damage. Class A, Class B, Class C, Class D, Class. What is Class A? It's a cosmetic damage. Paint came out, chips of concrete is not there. So not too much to worry with the structural point of view. Smoke damage, you know what I mean? Class B is minimal damage. You check some of it. Steel structures, you know, you see the pipe proofing coming down sometimes. Okay, in wood structures, for example, small little bit of charring. Depending on the material, you have different damage. So class C is some level of medium damage, right? Moderate damage is C. B is moderate damage, medium damage. Class D is much more damage. Class C equivalent. So each one of them, what are the conditions we put it? How much deflections you have? You move severe the deflections when you look at it hanging down, then it's either class C or class D, right? And so you can make rebars exposed will be either class D, partially exposed class C. So you can establish based on this into 5 classes of damage, and for each one of them, it's different levels of assessment. See, class A doesn't need too much engineering. The guy can decide, I will repaint it, I will refix the ground, right? So class B, however, a simplified empirical approaches can be used. Class C, you can use simplified approaches just based on structural heat transfer structural engineering principles. Class B or E, you need finite element advancement. That's very much. The reason is it's not easy to take 2 months and test it, produce it in 1 day, 2 days. If your bridge is under fire, you have to produce the result. And you can take one small coupons, you can take one span and bring it to the lab and test it is impossible. So this is why engineering assessment is required. And also, I think we said we looked at number of cases, as you know. So how many of them are minor damage based on the previous fire incidents? You know, very few will fall under class E when the fires happen. Much of them fall under B, C, and D when the damage happens. So they will be moderate to severe damage, but not fully collapse, local collapse. So then these thumbnails can be used. So based on the coloring of the color of the concrete, you can say something changes color. And whether the insulation has come out in the steel, that can give you an indication whether it's class B and class C. So you can use thumb rule, visual observations, as well as cracking, for example, can tell you, right? That will link you to what the fire exposure was. If there is significant falling, you should be more closely to hydro. So maybe a brick hit by a truck will cause huge petroleum fire, right? Whereas a small in a house or something, small fire. So that will, in fact, I can tell what temperatures after the fire is without if somebody explains to me without even going to the site based on the experience. So once you have that, so then if it is class A, you don't have to do anything, just field inspection is okay. Class B and C, non-destructive testing can be used by taking small coupons from the site. And testing right now, you have a lot of methods, rebound, ultrasonic pulsology, similar to that can be used. And class C and D, you know, you need to apply simplified analysis or advanced analysis approaches for B and D, wherein I will going to talk about that. So what is the analysis step? First step is to reconstruct what the fire was in the room. That's very important. So you need to think, what's the fire? What was the structure? Right? Once you know that, then it's easy, right? What's the duration? What I mean by reconstructing the fire, you need the temperatures approximate fire duration. So in this case, it's not that hard to reconstruct if you know if it is a hospital building. This room was burned, but there are many rooms in the hospital which are not burned. So this is a replica of that. You know what fuel load is immediately, right? Most of, if you go to a hotel room, all rooms will have similar bed, similar kitchen. So you can know reverse engineering, or even in that room, you can talk to the people who are owners and who are maintaining the building, apartment building. So once you get the reconstructed the building, you can come out with the fire curves. I'll show you that. Then observe structural members cracking, how much cracking has happened, how much falling has happened, how much insulation damage, and the color of the smoke can tell you, even the firefighters can tell you this. And also during the firefighting, these days firefighters use temperature guns. Automatically they have in their hard hats and helmets, it goes and it records what the peak temperatures are, if they are on time and stuff. That's also valuable, right? So then after that, once you know, calculate the fire, then you can use thermal analysis. Once you know the fire curve and you know the structure, what it is, you can calculate the temperatures in the cross section. Once you calculate the cross section, link it to how much concrete must have lost strength at that temperature at different layers. Once you know. Then once you know the strength of each layer of the concrete, you integrate it, you know the strength, you know the temperature, then you can get the residual capacity, how much it has. Believe me, it works because we tested out of class, we investigated outside buildings as well. It works. So this is the general procedure. And a lot of this is published, you can look at it. So this is the curve you want to establish during the fire. How do I establish? Based on the I know the room size, I know, for example, where the fire was burned. If there is a gas cylinder, you can add to that. You all do CFD modeling and advanced modeling, you can do that. Or you can use simple curves like this. Like, you know, many of you know the Swedish curves are the most famous curves in the Magnuson developed in 1960. Depending on how much fuel load means how much all this fuel load means carpets, this you can weigh, and you know how much kg per meter cube, as well as you know how much ventilation is their ventilation factor. So you can easily compare, get that and put it on this curve and use that. This is very simple predictive approach. Once you do this, then as I said, you do the thermal analysis, get the temperatures across the cross section. Heat transfer. You know because you know the fire turbine, you know that. Then you know the size of the element, you know the concrete thermal properties, you can do it. Then, in order to, you can verify that by doing some rigorous petrographic analysis and other things, see whether your temperatures will match, if it is a bridge or something, with the temperatures inside the concrete core base and the concrete change in color, concrete change in petrography. So you can develop that how whether your temperatures are within the range or not. This is cross checking. You can do that. You don't have to really do this. Okay. So once you do that, right, then once you know the temperature, so you know these curves. These are available. So this is strength retention versus temperature. So what is the residual strength at a given temperature? Each layer of the rebar, right? Once you, this is for rebar, this is for concrete, and then you can definitely do either simplified empirical approach, simplified approach, or one of the approaches which I am going to show, right? So once you do that, what's the simplified approach? Basic structural mechanics can be applied, right? Of course, you don't get exact results, but you are not looking for exact results. I mean, anyways. So we are close to 10 to 15% you can get in these simplified approaches because advanced analysis is much complex. So you set up the equilibrium equations. So just change it into P5. That means if there is falling, remember this is a original section. This much of concrete is fault here or here. You can remove that section, right? So your P reduces maybe, right? And your concrete strength reduces here, steel strength reduces here, AS, FYD. Where did you get FYD? In the previous graph, based on the temperature of the rebar level, you got the residual strength. So you establish the equilibrium equations, calculate the moment capacity, axial capacity, whatever you want, check against the loads you are going to come. So just like that, you do typical structural engineers, right? So this procedure can be applied to establish how much capacity is there. Now we use this, whether this works. This is a Brazil, a building in Porto Alegre, which is in the south of Sao Paulo. There was a building. I have collaborators there. There is a university there, an office building, 6-story. This was on fire, electric short circuit as usual, the country. And in this case, okay, you know, this building suffered very much damage for whatever reason. Typically, they use low-grade concrete and stuff. So I was involved with them. So basically, after the fire department came, they fought the fire, but not very successfully. There was a lot of damage, but they wanted to retrofit. And there were some number of buildings, huge buildings, you know, and in this big number of buildings, this compartment here, they were all burnt away, as you can see here. This was their approach. So we reconstructed, applied the approach I showed you so far how to reconstruct the fire. From fire, we went into temperatures in the beam, temperatures to strength, strength to capacity. So then the building was retrofitted. I have all the step by step, but because of lack of time, I'm not showing you this. If you have later, I think we can talk about it. But here, recently published, and the building is back to us. BN engineering, right? And we compare this with the research as well. We did petrographic analysis because the building, they were not in urgent for repair. So we compared whether this methodology works in estimating temperatures. So then this method though works, it's not exact as it's. But these days we have computers, we can use advanced techniques to get bit more accurate results. Why not? Reliable results. So you have to use advanced analysis because in the previous one you cannot account for spalling, you cannot account for temperature, speed, bond. These are some of the issues with modern materials, right? So for example, bond used to be very good between concrete and steel. Concretes of 1980s. So bond reduces thin layers that come straight compressive strength. So modern materials, right? So I say that concrete and steel are made for each other, but not the modern concretes. The bond decreases at a different rate. They are not compatible at more high temperature. So you need different properties, right? So that kind of stuff you can not use in this simplified approach. So what's the alternative? You can do advanced analysis. As I told you before in the experimental studies, 3 stages of analysis. If you want to do the finite element modeling, once it's set up, First one is you need to know what is the level of the structural capacity just before the fire starts. This structure. Then subject it to fire just like before, right? We create the fire curve, what it was in that room or in that building, and then estimate the temperatures of the concrete steel members, and then followed by you find out the analysis approach, you find out the capacity. Right, so that's the three-stage approach. It's the finite element models can be applied. You can account for theory in all the stuff. So if you are retrofitting a major frame, a major structure, or a building, so this can be very useful for doing this. You can create these fire curves. So this is the flow chart to do this. As I mentioned to you, stage 1, stage 2 is during the fire, just before the fire, and after the residual phase. 3, 4, 5 days after the fire, how much then recovery happens, right? So when you subject this stage 1 here, it catches fire, and this is stage 2, it cools down completely. Then stage 3 is up 3, 4 days, complete recovers its full strength. So in this case, it is possible in stage 1, basically, you establish a response and find out how much just before the fire starts was initial deformation of the structure. And you need to superimpose that during the fire, because that's the residual deformations will have an effect on the performance of the structure during the fire. So for that, basically you carry out but you don't, you cannot use just building code, IS 456 equations. You have to use finite element analysis to get the deformations, not just the stress. You need to know that residual, you need to know that the deformations and the service load just before the beam, because after 50 years, that strength, whatever was used in the design stage is useless. You can take a core, you can do that. Also rebar, the reserve, any reserve capacity is the rebar, that can be used, tension stiffening can be used, strain hardening, all that can be imposed into the analysis. Now, then you do the stage 2 analysis, thermal analysis, right? You know the thermal properties of fabric. They don't change heating and cooling phase. So the properties during this phase, but mechanical properties, you need stress strain curves, you need basically the bond slip relations, you need falling, all this can be incorporated, and so you can generate that during stage 2. Stage 3, after the fire exposure, what properties you need? These are called residual properties. Basically, what are the residual properties? You heat the specimen, leave it to cool to room temperature for 2 hours, and then you test that cylinder, that's the residue. During fire, it is like heating phase. When it is still burning, you test it, how much strength it takes, and develop the stress strain relations. So at each stage, it's different set of relations you need to use. Stress strain curves, as well as thermal properties in stage 2 and residual properties here. So how do we apply this? So I just have a case study here. We tested 2 beams, one subjected to this fire. This is short arc fire. This is, we call it long fire or long fire. So short B1 is subjected to short fire, B2 is subjected to long fire. It's about 4.5 meters between the support. This is the concrete beam, and so you discretize in abacus, lances, anything you could use. Then once you discretize, stage 1 of the analysis to get, this is the deformations in the beam just before the fire starts. Right? You don't know after the fire what happened when you go and inspect, but you can simulate that on the computer based on the load. You know in this building what the load levels are, that load, day to day, you can estimate that. So you get, and you superimpose those deformations here. See, I superimposed here. These are the temperatures, the beam, various points in the beam being measured at rebars, quarter depth, half depth. So you see this is in the rebar, this is quarter depth, half depth, and these are the temperatures. Okay, during the fire, and this is how nicely the structure. This is the short arc part, this is long arc. So this is the leftover residual deformation after stage 2. You superimpose these residual deformations to find out. Then you do unknown analysis, again using ANSYS, same program, same abacus, same model, but this time you are just evaluating the structural capacity of that beam under the condition that this has this much reinforced deformation and this beam has this much reinforced deformation. This is the load or the capacity which is left over. So now, if that beam has to carry more than 180 kips, let's say it has to carry 250 kips. So then you have to strengthen the beam from 160 to 250 or 180 to 250, depending on the level strength after the residual phase. Then you increase it to the original capacity to open the structure. Otherwise, it's not safe, right? So that's what I plotted. So there is a building here. This is the moment capacity with 500. So after 10, this time is not in any units. After 10, 20 years, there is a 5. So at different stages, in fact, we update this for a building in Iran. So you can see that. So this one collapses. So you cannot do class 5 damage. But there are a number of beams at different levels. This is the local collapse of one beam. The building didn't collapse. So this building, this is the residual capacity left. This is the residual. This is the residual. If you want to increase, this much is the retrofitting needed. This much is the retrofitting. So you can develop how much retrofitting is needed to go back to the original equipment. So what are the repair methods? So there are a number of repair methods which people commonly use. Okay, if it is class A and in some cases class B, it's just grouting is required, painting, surface cleaning, the look back, right? Finishing touches, nothing else. In class B, C, D, E damage, you may have to keep structural capacity in mind. You may have to enhance the capacity to bring back the original capacity of the structure. How do you do? Either you can use fiber reinforced polymers. This is the latest technique used in a lot of applications, very big retrofitting. That's has been extensively used after non-bridge earthquake and other applications, but as well it works very well. Now, molded side plating method, steel, this is for steel plates, or replacement of concrete reinforcement methods, or externally you can freeze resist, steel wrapping can be used. So number of things can be used. Okay, and if it is class C damage, maybe it has to be demolished either locally or the whole structure. So if you see here, repair strategies. So after fire, basically you have to ensure that the structure has same level of structural safety and fire safety. Many times people forget. They strengthen it to get the structural safety, but before the beam was okay. But if there is steel structures especially, you have to make sure that you put sufficient insulation, just like before, and you put steel plates on the bottom that weakens the structural safety. So even for a concrete building, before you may not have needed the fireproofing, but once you put the steel plates, you need to make sure it is fireproofed before occupancy. Otherwise, if there is a fire, the steel will disintegrate quickly. So, right, and short breed is a possible way. Some of the applications strengthening of our CFRB, for example, here. So, for class B and C, that way approved materials is recommended. Additional steel reinforcement, steel ring plates, jacketing of the steel columns is very common. Okay, so make sure fire resistance ratings are also satisfied. So, in summary, reinforced concrete structures exhibit good fire resistance because of their low thermal conductivity, high heat capacity, as well as lower degradation strength property. Right? So structures following fire exposures, it can be grouped into 5 classes, class A to class D. So where in class E is building might have to be demolished. Class A, not much needed. Class B and C and D has to be analyzed using advanced methodology if you want to get the reliable capacity. You can save a lot of money. If there is a building, each building, fire burns in some compartments, firefighting happens. Some beams require 40% increase in capacity, some requires 40%. Fire damage is not too fun. You cannot apply to this. So by setting it up, you can save a lot of money as well by doing engineering. You spend some money for engineering, but you save on the materials. It's sustainable as well, right? So advanced analysis technique is the way to go, and right now, with all the availability of abacus and all this, you apply three-stage analysis, it can be very nicely modeled and developed, right? And there are a number of critical factors that influences the post-fire residual capacity of the members, including fire exposure, what the load level is, what the restraint effects are, right? And following a fire incident, fire damage concrete members, they might satisfy the design limit state, but they may not have the original reserves. In fact, they survive that fire because of the original reserve strength. We generally provide significant increase in cross sections, additional. Designs are always conservative. They won't have that conservative. So if you want to maintain, go back to the conservative, it has to be retrofitted. That should be kept in mind. So that can be possible. So I would like to acknowledge these are our PhD students and postdocs who worked with me over the years. Also funding agencies. USAID, I think, has funded this project. So a number of other companies and National Science Foundation, I would like to thank them. And it's very hard to find information. We have a chapter in this book on how to evaluate some of the stuff I mentioned to you, not only for concrete structures, but for steel structures, wood structures, FRP structures, tension structures. It's very, very latest state of the art. And also, what are the research needs going forward is given in that chapter, one of the chapters. Okay, so thank you very much for your attention.
Like to take a few questions?
Yes, definitely.
Let's suppose if a transport tunnel.
Yes.
Suppose if a transport tunnel under hydrocarbon fire for 60 minutes.
Yeah.
And after fire, when we observe the exposed face of the transport tunnel, virtually it is a concrete tunnel. So there is no visible damage on the surface of the concrete. So what is your opinion? It should be stopped for the usage of the public transport, or it has to be stopped?
Very hard question. Because tunnels, if it is subjected to severe fire, hydrocarbon fire, let's say two cars collide inside. The fire is likely to reach 800, 700, 900. Not that bad. And the duration of the fire is quick. But let's say it's two oil tankers colliding or even one oil tanker colliding. Temperatures likely go from 100 to 1300 degrees centigrade. And if the firefighting didn't happen quickly, then the temperature duration also for the first 40 to 50 minutes, though the fire came down in 60 minutes after firefighting, that's severe. So inside there may be microstructural damage. Before opening, at least they should be able to do some pores, small pores, drill the pores of the tunnel. Just to look at more than one pore. Not only from the fire damaged area, this is where tunnel is affected. This is not affected. There is no burn happen. Take this course, take this course. That's what you have to compare and contrast. You will know this difference between this and this at different depths. You can do microstructural analysis, then only you can show. The reason for that is it's too risky sometimes. Though I think, as you mentioned, if outside there is no decoloration too much, it's not there, it's safe, but I think you have to take some precautions. Yeah, please. advanced analysis is better than simplified analysis. That's why it's advanced. So, but in a case like that, like Kamal mentioned, basically, so if there is no outside too much damage, right, if everything is looking good, if you want to reconfirm simplified analysis, you cannot. But on the other hand, if the rebars are exposed, or if there is significant falling there, if you can see noticeable reflection, right, in beams, for example, right, or any lateral twisting of the beams in state structures, local buckling, then immediately you cannot do local response, simplified analysis. Simplified analysis is sectional analysis. You take two sections, critical sections, and make sure. Advanced analysis is at the member or even the global level. So system level, at least member level analysis needed to get the level. So that requires judgment. Initial, some kind of a judgment. Yeah,
Very nice presentation. My compliments. I have twofold of questions. First of all, how you assess the residual capacity of rebar post fire, and thereafter how you incorporate in the model to assess the capacity of RC element post fire.
Sure. So, as I said, so there are heating based properties for the rebar well established. Residual phase also there are, but typically rebars they recover almost 100% of the strength. If during the fire the rebars did not reach 400 to 500, if they have not reached, let's say there is a fire, so temperatures go up in the rebar. As long as the temperature is not of the fire, but the rebar level itself, if it is 400 and below, they regain the full strength. But if it goes beyond 400, they decrease about 10 and 600 or 700, then cool down. Let's say 600. Then they will lose about 10. There are guidelines for that. So you use 10% reduction in not of so that 10% reduction. Let's say rebar is 300 megapascals. 400 you use. So 400. So for 400, if it goes to let's say 550 degrees centigrade, so that means and then cools down. In the heating phase itself, so 550, the heating phase at 550 rebar has lost 50%. So it will have only 250. But if it completely recovers, then it will have 10% less than residual. 10%. So there are curves I showed in the presentation, but quite small, so you can look at the papers and stuff. So that properties are there. That's the one you have to use. Same thing with concrete as well. So that's why it has to fully cool down, not necessarily just after the fire. You cannot look at it. Fully, it has to come back and gradually regain.
There is one online question.
Oh, please, please.
So how spalling can be incorporated in finite element analysis and potentially in commercial software?
Oh, that's the big question. So basically, you can incorporate. There are two ways of incorporating. Simplified way and advanced way, always right. So in the simplified way, which we started in 2000, early 2000 when we started high-strength concrete work, in abacus and ANSYS, if you use, there is what is called killing elements approach. You kill the elements. You divide the both sections into hundreds of elements, right? I mean, finite element means it's small. In the mesh, at the edge, as soon as you find this reach 350, 500 or something, if you know that's the criteria, you remove that element. At 20 minutes, this temperature reaches 350. You have to do time-step analysis, not one time. At 15, nothing happens. 16 minutes, 17 minutes, 18 minutes. This much is reached 350, you can remove that. You can kill that element. So the remaining structure is this. At 42, this much reaches, so this part is gone. That's what happens in the test as well, if you notice, layer after layer. So you can remove that. That's the kill elements of it. That's the easier approach. Right? So just measure the temperature. Second analysis, much more complex, where you need a lot of data, not just the temperature. So why is this element fall? Because falling happens because inside there is pore pressure. Water becomes steam, it wants to get out in the concrete. So when it reaches 100, 200 starts to go up. Around 300, 400, the pressure converts itself into tensile stress. When that tensile strength is less than the tensile strength, it pushes it up. So you have to find out the tensile strength. You know what I mean? So what the tensile strength will do? More pressure. And once you do that, you incorporate, and then the model, Rebecca cannot handle. You are right to separate. My students do it. I don't know subroutine. Link it. Then it can model, it can monitor. That's the realistic approach. That's what really happens in the structure. The temperature approach is a very simplistic approach. So it can be done today in Abacus coding with little bit of MATLAB code writing, whatever, you know. So that can be done. Sure.
While assessing the residual capacity and those things, consider only strength properties or durability properties also, like corrosion, carbonation of concrete, chloride, or sectional loss in ductility loss in reinforcement.
Yeah, no carbonation and those properties, but for sure, loss of the suction we consider those falling. Yes. But we consider we need lot of properties even to model that tensile strength pore pressure calculations. See, you need tensile strength. We neglecting at room temperature, but at high temperature. So why there's not if you see this, whatever common sense tells you, lot of times is not right. Sustainability is not good for fire. Sorry to say that. I know, unfortunate, you know, because you are reducing your cross section. These days, you have very section. We are making holes everywhere. Hollow core slabs. And our bridge girders used to be very nice. Now they are all, everyone wants to be model shapes, unfortunately, including our structure. It's very bad for fire because thermal mass is the one which used to give us good fire resistance. That's going away. We never gave importance to tensile strength. Tensile strength is the most important parameter. In fact, US, they were laughing when I was making presentation because in the presentation I was making an effect of temperature and tensile. They said we don't even consider at room temperature, at elevated temperature, it will go down. Even at room temperature, we consider zero. Why do you want to do this research? But that's the most important property we want to prevent the spalling. Higher the tensile strength, it performs better. So many of the wood, for example, wood columns, we have used a lot of wood. It can last 2 hours in fire without collapse. Steel column collapses in 20 minutes. I can give you about 100 cases where fire, everything what we think. I was telling you when I looked at it, was on the desk. Steel stud walls, if you put insulation, fire insulation, very bad in fire. Remember, this is fire protection insulation. Whereas if you leave that without insulation, heat comes and goes away. If you put insulation, heat gets trapped between the 2 studs and it damages the studs in 20 minutes in local cooking time. So there is a lot of things, anomalies. So I think it's very hard to include everything. Yeah.
Any
Okay, become porous, as you said, you will falling for the vehicle fire event. It will become very much porous. Suppose after a post fire assessment, found the structure is suitable, like considering the kind of reduction of the area.
Yeah.
Wise is okay. Yeah. But suppose those structural elements are exposed to the other environmental conditions. Suppose in the outside you will be extreme weather events or anything like that. So there it may for some other kind of failure, like suppose it was overraid or something like that. Yeah. How we can take care of that kind of thing?
Yeah, during the residual test, you know, which is done is keeping in mind the structural capacity, structural ductility, everything can be done here. But if it is other condition like corrosion, sometimes when you put something around the concrete, when you fix it, that might lead to corrosion, for example, right? Yeah. So I think you have to consider that separately. You can make it on the top layer. You can have grouting, for example, if possible. Grouting is the easiest thing. You can use corrosion. It can be used a mesh. You can put a mesh and then build that can be done.
Okay, last question.
In your opinion, which is better, like from the fire performance point
the better is outside, inside, or inside the cavity, or what research needs to be done in that area?
Yeah, there is no answer. You know, the building I showed you in Great Towers in UK, which collapsed, 79 people died. So after that in UK, 4,000 buildings were renovated. They put this, they paint everything and the cladding, insulation and the cladding. So Dubai, there are Dubai and Middle East, there are 1,000 buildings. And so they were looking for contractors to do the work quickly, fixing, because once this happened, the fires made it happen. You must have seen in Dubai, there were a number of fires once, 4 years ago, and a few years there as well. So that's happening because of the cladding material, this insulation material they use for energy saving. I don't know whether it's good to put inside, outside, at least inside there is more probability of fires suddenly catching. Outside, at least it might grow to the next person stuff, but outside is better than the inside. From the safety, entirely from the fire safety point of view. But those materials, there is a lot of research going on, especially in Europe, to change those cladding materials. There are no testing standards as well. How do you assess it, then spread? There is a significant opportunity in this area. Yeah, but yeah, go ahead. Which one is it steel? It depends. Yeah. The big wall, resist wall is typically better if you provide insulation. There are things like gypsum wall. That's still the best material. Rather than putting all this cladding and stuff, if you base it on gypsum and not the regular gypsum wallboard you get in the store. It's very cheap. There is fire-rated gypsum wallboard. It's 4 times fire resistant than this one. And there is super fire-rated gypsum wallboard, 10 times expensive. They use oil industry and the rest of it. Still, gypsum wallboard is very good. Rather than most of this cladding and other this boards and that kind of stuff. Yeah. Green one, I don't know. The market, they come out with commercial products without too much research, too much experiments. They don't want to fund any research. It is not. No, I don't think so. Yeah. From my point of view. Thank you. Yeah.
Thank you, Professor. You have generated a lot of interest, and I'm sure all of us has gained a lot of knowledge about fire engineering in buildings. And my colleagues, particularly young colleagues, they are interested. Thank you. Let us again appreciate you. This is the number which you have. Now, as a appreciation, as a token of appreciation and for remembrance, we would like to present a memento to Professor Kodur. I request our director to please present the memento.
Thank you so much.
It's a modern Kerala temple. For those who want to know, it's a beautiful model.
Place where I want to go and thank you.
Now, I request my colleague, Dr. Pandike Ram, to propose a vote of thanks.
Thank you, sir. My dear colleagues and CSIR family, it is my privilege to propose a vote of thanks on this expert lecture series. My heart fills with lots of gratitude and respect of our distinguished speaker, Professor Venkatesh for not only sparing his valuable time for us to praise this occasion, but also enlightening with their commendable talk on structural fire engineering. Thanks, Professor Venkatesh for clearing our concept and enhancing our knowledge and understanding. I really owe you a lot. I want to thank the third year of this event, our respected Director Sir, Professor R. Pradeep Kumar, for leading and inspiring us in working towards the goal of conducting this technical lecture. I am thankful to him for his huge support all the time. No will take place without a hardworking leaders. It was the dedication of enthusiasm of our leaders and organized chairperson, Dr. R.S. Karade, event and lecture committee, Dr. R. Dharmaraju, outreach, dissemination and service office, and Dr. Harpal Singh, coordinator of fire safety engineering, made this event a huge success. I extend our gratitude to them. I am running short of the word to express my humble thanks to the technical team, media person, and administration who have devoted lots of time and energy to this program and made this event more beautiful. Thank you to all of your presence here in this expert lecture series. Thank you so much. Thank you.